Hey everyone, today's lecture will be about interactive problems. So let's get started. What is an interactive problem? That might be our first question. Well, there is a simple way to look at it. Basically an interactive problem is a two-player game. That's it. Why do I say that it's a two-player game? Well, basically there are two players. One, our program, and the other player is the judge. And what are the rules of this game? Well, the rules of the game are given in the interactive problem statement. But basically, there will be some way in which our program and the judge exchange information both ways, basically. And so that is why it is more like a two-player game. That's it. That's the basic of interactive problems. So just to make it clear, in a typical, let's say, normal, so to speak, problem, or batch, maybe, let's call it a batch. In a batch problem, which are the most common ones at ICPC, you have an input, and your program, it does not necessarily have to read it all at once at the beginning, but in principle it could. Basically, there is an input, you could in principle read it all together in one go and have the whole input. Then you just make a calculation, you compute the answer, and then you output it, and that's it. That's the standard batch problem. Well, in an interactive problem, this is not enough because there is interaction going on. So the model is quite different, actually. What is the model in this case? Well, your program, this is the program, is given some input, but not the whole input, basically. It's given part of the input. Basically, this is like asking a question or posting a situation or making a move in a game. So this is the initial setup. And then the judge will wait for our program to do something, to respond, to answer, to make a move. And our program thus will have to do something, which we can think just as before. In a normal batch problem, this would be just doing output. That's what we do. Well, in an interactive program, that output is something that we have to do. We have to answer a query, we have to make a move, we have to do something. Then in response to that something that we do, the interactive judge, that is, will typically send more input. That extra input will codify what the judge is doing. So maybe it's asking another question, maybe it's making a move. That is why it's like a two-player game. In a two-player game, there are turns, there are well-defined turns, there is a protocol of how to move, and each time one of the two players makes a move according to the rules of the game. Well, that is exactly the situation in an interactive problem. One player is our program, the other player is the judge. They take turns making a move, which is doing something, typically writing output or giving our program input or calling a function or something. And the precise rules of how do we have to interact will be given in the problem statement. So that is why basically every interactive problem is like a two-player game. But there are some typical patterns that we might expect. So let's mention them. The first pattern is, well, of course, a two-player game. This is basically what I already said. Well, you can think of every interactive problem as a two-player game. So if the interactive problem is about a two-player game, then this is trivial. We don't have to think. For example, I don't know, maybe the problem is about NIM, the well-known game of NIM. And the task is actually to code a program that plays NIM perfectly and wins against an opponent. So our program will have to actually make a move in the game of NIM and then wait for the judge to give us its move and then respond accordingly. So we don't have all the input at once because the opponent move will only be given after we make our move and might depend on our move, of course. Well, what other common situation do we have? Well, another common situation for an interactive problem, which is not so which can be avoided, so to speak, is those of online queries. Just to be clear, when you have a problem about queries, where you have some situation, some input, and you have to answer a lot of queries about it, the queries could be online or offline. Offline means that you have the whole input and all the queries in advance. So you might do things like read all the queries and sort them in order to answer them in order. That's very common. Well, that's offline. But when you have online queries, that means that you are given one query at a time. So in this kind of problems, we must answer every query before we can receive the next one. We can't read all the queries that we will be asked before answering them. And that makes some algorithms impossible. So in terms of the two-player game, when we try to think of this as a two-player game, it's like the case where we have a problem with online queries is like the judge strategy is fixed beforehand, because the judge will just ask some questions to us and that's it. It will always ask the same question. The detail is that this might be an interactive problem because we don't receive all the input at once. So it's not really batch. We cannot see all the queries before. There are some batch problems that use encryption or something to force online queries, but this could also be forced with an actual interactive problem. So I'm including this pattern here. And in this common case of interactive problems for online queries, actually our strategy is also fixed. So our strategy is fixed. It's like we have no choice, because all we have to do is answer the query, which will possibly have a unique answer, but it doesn't change state or anything. There is no reason for the judge to change its questions based on our answer in this kind of problem. So it's not really a game theory, although it can be seen in this way like a two-player game, and it is an interactive problem. This pattern, when it is used for online queries, which is very common at IOI, for example, is actually more a data structures problem. And it will be a data structure problem. And it is very common that persistent data structures will help in this kind of problems. And then of course the third common pattern of why you might find an interactive problem are those interactive problems where there is a secret that we have to guess. In these problems, there is some hidden information about the world that we actually don't know, and we have to discover it. And the only means of discovering is asking questions. So it's sort of the inverse version of the online queries problem. It's like the judge is the one that will answer our queries, but we are responsible for choosing which queries to ask. And our mission is to use those queries to get information and discover the hidden secrets at the end. This is a very, very common pattern of interactive problem. So although this one can actually be seen as a two-player game, because we are playing against the judge, and the judge is trying the judge wants us not to guess, and we want to actually guess the secret by asking questions. But this is such a very common special case that I want to mention it, and we will see some examples of this one. So we can ask questions, and the judge answers, and we have to discover the secret. And there are like, let's say, two sub-cases. The judge might be adaptive or not. If the judge is non-adaptive, that means that the secret information is actually really fixed beforehand. For example, it might be a password, a secret string that we have to discover somehow asking questions. And maybe the password is, I don't know, car. Okay, it is fixed beforehand, and the judge will actually not change it. That is one option. and so the judge implementation is just knowing the secret, and when we ask a question, answering it. The other option is that the judge is adaptive. In this case, the judge might actually change the password underneath without us knowing, so there might not be an actual unique password during the whole run. But the adaptive judge should not cheat. So at all times there might be a set of possible answers, and the judge has not yet decided which the answer is, and will decide based on our questions, trying to make us waste questions and take a lot of questions to resolve. But there has to be at least one answer. It cannot lie, so to speak. So, for example, if your game is, if the secret is just a number, and we are asked, and we are allowed to ask if the number is lower or higher than something, well, we might ask, is it larger than 10? And the judge says yes. Okay. We might ask, is it lower or equals to 10? Well, the judge says no. Okay. We might ask, is it larger to 11? And the judge says no. So now we know that it must be 10. But it must be 10. No, it must be 11, sorry. Yeah, it has to be 11. That's the only option. So maybe we ask, is it 11? Well, now the judge cannot answer no. The judge is trying that we don't guess, but here, if it says no, then there would exist no possible secret satisfying the questions. So the judge here is forced to answer yes. Even if it is adaptive and it is not committing to a single answer, maybe the judge tries to say, oh, no, always no, you're wrong, until the last possible time, then that would be an adaptive judge, and we might need to be prepared for this. But unless the problem is actually broken or something, an adaptive judge will always answer in a consistent way, so that there is at least one answer yet. And typically the statement or the rules of the competition should ideally state whether non-adaptive checkers are allowed, because sometimes we could have typically probabilistic solutions that have a very high chance of working if the judge is non-adaptive, but which could easily fail with an adequately programmed adaptive judge, because an adaptive judge is like an opponent. It tries to deceive us into changing its mind, so that at the very last time we get to the solution. So it tries to make us use many questions. Oh, and I think I forgot to say it, but in these problems, typically we are given a limited number of questions. So we have a budget, so to speak, of questions. And so maybe the problem says you can do at most 100 questions. And so you have to think how to find the secret with that few questions. So in many of these problems, time limits are not that important, because the actual resource that we try to avoid using a lot is the number of questions, not the runtime. It depends. Sometimes we need a lot of time to calculate the best way to ask, but generally the number of questions is more important than the runtime. Now, I will mention that two contests that very regularly feature interactive problems that I like a lot and are great contests are the IOI, the International Olympiad in Informatics, and the Google Codejam. So I really recommend you to check both past editions for problems if you want to practice with interactive problems. Those are great problems. And let's talk about the interaction protocol, because well, in a normal program you just read and write to standard outputs typically, and that's it. So how is the interaction done actually? Well, there are two main ways. One is with functions. there are some special functions in your program that are not provided by you, but should be provided by the judge. And you just call those functions in order to ask questions to the system, for example. Or maybe you provide some functions which the system will call when it wants you to make a move to do something. Those are typically much easier for the contestant because in interactive problems, it's quite a hassle to actually implement the interaction. And for the contestant, it's easiest if it's just, well, there is a function and call it and it will return such and such a value, and that's it. For example, in my previous example, maybe there is a function is the number larger that takes an int and answers a bool, true or false, and you can call it many times, and that's it. That is much easier. So as a contestant, it's better for us to have functions. The function method is typically used at the IOI, at least for recent years. Maybe 15 years ago it didn't, but in the last 10 years it has been most common at IOI to use functions. While at other judges, like Codeforces and a few ICPC regionals with interactive problems, CodeChef, CodeJam, typically interaction is made with input-output. So this one is much easier for the judge system because when you use functions, you typically have to give the function signature to the contestant, and you have to write special code in many languages when the many languages are allowed. So as an organizer of a contest, it's much harder to just to provide all those functions and to code them or to make a code that automatically generates them because it depends on how many languages you have. The more languages you want to support, the harder. So it's much easier for the contestant, but much harder for the organizers. That is why almost all competitions with interactive problems use input-output, because that doesn't change depending on the language. But a caveat is that when you have input-output used for interaction, that means that instead of calling a function to do something, you would have to write your function call, so to speak, and the parameters in a specific way to make the query. And the judge will respond, and you'll have to read the response, and that simulates like calling a function and getting the return value. You should remember to always flash your output in interactive problems, because otherwise, if you don't flash, maybe depending on the language and how exactly you're doing it, maybe the output stays in a buffer and is never actually sent to the system, and so your program never terminates, and it's probably time limiters exceeded or something. An easy way in C++ to use endline, endl, when you send endl to console out, it automatically flashes. And if not, you can, just to be sure, as a safety measure, you can always flash explicitly with cout.flash. But whatever you can do in your language, just make sure that the output stream is flashed. Otherwise, you might get time limit because the system never receives the actual data. So it thinks that your program is waiting. Now, all of this leads us to the first key idea that I want to transmit to you. In interactive problems, always create functions that abstract the interaction. You should not use input and output directly, asking the question and reading the answer and flashing the buffer and checking, because a lot of time the interactor will also tell you that if you have some mistake, it will return -1, and you should immediately abort and do like exit 0. All of those details, you don't want to do it in your main program, because it will make the code much harder to read. So basically, create a separate function. So for example, if you can ask if a number is larger, and the way that you have to do it is first write to cout the string larger, and then a space, and then you have to write the number, and then you have to flash, and then you have to wait for the answer, and the answer will be no or yes, and you have to check that and convert it to Boolean. So instead of doing all that in your code, you should code the function larger, which just returns a bool, and you pass it an int. that's it. And inside the implementation, the function will take care of all the interaction details. That will make your main code much easier to read, to debug, to code, to understand. It will be better in every way. So always do it, because like I said before, the use of functions is easier to code with, so it's better for the contestant. And the reason that input output is used instead is just because that's easier for the system. So code the functions and change the language to your advantage. Do not do cout every time and deal with, because the interaction protocol sometimes might be not so easy to work with. So it's better to avoid it entirely and encapsulate it into one function. Also, if you have a bug or some detail you forgot to flash, whatever, some detail in the interaction, you will probably have that in many places in your program, but if you have it in a function, you can easily change the interaction details only once. So the first advantage of doing it this way is that we get to the good case functions instead of input output, like I said before. The second one is that the code is nicer, and that is great because it's easier to debug, it's easier to write, and that will help you a lot, especially because you will probably spend a lot of time debugging code. So it's good that it's easier to read, and that will make it much easier to find actual bugs in the implementation. It is very easy if you don't separate into nice functions the interacting part, to write a long code where it is hard to see the parts, because you see the details of the interaction everywhere, and it's hard to find the actual bugs. It's very hard to debug them, so avoid it at all costs. It seems like such a simple thing, but actually, if you've not done interactive problems before, maybe you just say, oh, okay, it's too simple, I will use cout directly, and then everything is much harder to read. I guarantee you, believe me, you will have less wrong answers this way, much less wrong answers this way. Well, another interesting advantage is that you can add functionality when you separate it into functions above the basic query. Because, for example, you can add a cache memory, like a map or something that remembers the query. So maybe in your main algorithm, it is easier to implement it if you just always query. And maybe you have to do the same query more than once because of the way your algorithm works. It doesn't remember that it already queried it before. But maybe you want to avoid doing multiple queries more than once, because you have to use as few queries as possible. Well, one very simple way is to just put a cache memory in the function, and that's it. You will first check, oh, have I already done this query before? Oh, yes, I did. So return the answer immediately. I know it. Otherwise, actually check it by writing and doing an interaction, and then save it into memory for later. Also, you can add extra checks, which is very common and very useful to save, to make the code easier. For example, you might have a problem in a board where there are some cells, and some cells have, I don't know, grass or walls or whatever, and you can query cells inside you don't know the board yet, but you can make queries asking, well, what is in this cell? And the system will tell you, oh, a wall, for example, something like that. But it is illegal to make queries outside the grid. If you do a query outside the grid, for example here, then your program is automatically deemed wrong and you lose and you can't, sorry. But maybe for your implementation, it's much easier to just think, okay, outside the grid, it is always walls, and I would like to ask queries there because it's easier to implement, maybe. So then what you can do is you can go to the function that implements the query and first do some extra checks. And if you are querying outside of the board, then you don't actually do an interaction with the judge. You just answer, oh, there's a wall. So you have like, you're inventing extra answers that the judge is not will not give you and will say, oh, if you can't ask here, if you ask here, it's wrong. Well, you can change the function so that it is allowed and it doesn't even count as a query because it will never get to the actual judge system. So you get all of these advantages. So there are basically no disadvantages to using functions instead of directly doing the interaction. So I would recommend you to always encapsulate the system interaction into nice functions. So that way we get to the key idea number 2, which is to create higher level queries using lower level queries. So we already have some function or multiple functions, if there are multiple queries allowed, that encapsulate the problem's query. That's great, and we can use them. But maybe we can build a more powerful, higher level query by actually doing underneath several lower level queries, which are the ones that the problem gave us. And that is great because that way we can build an increasingly rich language of questions that we can ask about the problem. So this is a great idea, and it's much easier and much natural to do it once you have created functions in the first place. So let's do an example of this. Let's suppose that we have a problem where there is a tree. It is a rooted tree, say. So maybe there is a special root. Let's say that this one is actually the root. Okay, good. And so we want to know whether a node is descendant of another. It might, for whatever reason in the problem, it might be good to know, well, given two nodes, A and B, is it the case that A is a descendant of B? Maybe it would be useful for us to have this question possibility. Now, let's assume that the tree is not known to us. It is secret. We might not have the tree, because if we actually have the tree, we can run some algorithm like DFS or something and pre-compute things, and we can quickly answer this query. But maybe we don't have the tree. We don't know what the tree is, but we are allowed to ask questions to the system. Let's suppose that, for example, in this problem, in this imaginary problem that I'm making up, the system allows us to query for the lowest common ancestor of two nodes. So for any two nodes, X and Y, we're allowed to make this query. So we can solve LCA for two nodes. For example, if we ask, so this is the root, and there is a well-defined root. I don't know if we know it or not, but there is a well-defined root, and that defines which nodes are descendants. For example, these are all the descendants of B, and these are all the descendants of A. Oh, sorry, this one is also a descendant. So yeah, if we have the LCA questions, maybe we can ask what is the LCA of X and Y, and then we get this node as an answer. Or if we ask here X and Y, we will get this one as the answer, etc. How can we use LCA queries to solve this this question of whether one node is a descendant of the other? Well, there is a very simple way, because if, for example, we can ask the LCA of A and B, actually. And by doing so, we will get an answer that depends on whether A is actually a descendant of B or not. Now, if A is a descendant of B, then B will be the LCA. And it's if and only if. If A is not a descendant of B, if A is somewhere else in the tree, say here, then B will not be a descendant of B will not be an ancestor of A, and so it is impossible for B to be the LCA. So this question solves our problem. This is completely equivalent to asking whether A is a descendant of B. So we can actually implement it, and now we will have an extra function, descendant AB, which asks the questions of whether A is a descendant of B. And underneath, it actually makes a call to the function which computes the LCA. And that function is the one that actually makes the interaction with the system. So in terms of budget, the question of asking whether A is descendant of B costs one LCA question to ask. So it costs the same as a direct calculation of LCA. But having it implemented directly makes the code easier to read than having to write this everywhere. Here you have to read and check and understand and say, oh, okay, it is checking whether it is a descendant. And maybe another more interesting example that we might want to solve is the following. Let's suppose that we want to compute LCAs. Okay, we want to compute... No, okay, first let's solve this one. We want to solve the query. Is X in the path from A to B? So, since there is an underlying tree, even if we don't know it, for every two nodes, there is a single path between them. Let's go here. For example, for any two nodes that we can imagine, A and B, we don't know what the actual tree is, but the drawing will look something like this. There is somewhere, okay, let's make it not so far away. There is somewhere the actual LCA of A and B. Okay. And some path up to the root of the tree. This is the situation. And the path between A and B will always be like this. From A to the LCA and from the LCA to B. So if we want to check whether X is on the path, we have to be able to know if X is one of these nodes. So using this drawing, we can characterize and check that actually, if we look at the ancestors of A, which I will paint sort of white here, and we check the ancestors of B, which, okay, let's say we use magenta. We're almost there, because if we take the union, if we check those nodes that are an ancestor of A or B, that's the nodes in the path in green, except for these ones, which are the ancestors of the LCA. But then we might also add the condition that we want our node X, in order to be in the path, to be a descendant of the LCA. So it must be in the subtree rooted at the LCA. And if you take care of this, I've actually said ancestor or descendant 3 times. So our condition could be, for X to work, we need 3 things. X must be a descendant of the LCA, and it must also be an ancestor of A or B, one of both. So it has to be an ancestor of A or an ancestor of B, so it will be in this part. But then in order to avoid these ones, which are too far away from the path, we can also ask X to be a descendant of LCA. So in order to call the function path X, A, B, which checks whether X is in the path from A to B, we can actually write the condition that we want. What do we want? We want X to be a descendant of the LCA of A and B, which the problem allows us to ask. And we also need one of 2 conditions. We need either that X is an ancestor of A or an ancestor of B. And we can also write this as A being a descendant of X. That's the same. Or descendant BX. And that's it. So with 4 queries, we are actually we have actually built up, and now we can create a function which has a higher level query, which asks whether one node is in the path from A to B, using only 4 of the primitive basic queries that we had underneath, because we had to use 3 desk calls, which each one calls LCA underneath, and 1 extra call to the LCA. This can actually be improved to 3 queries. And this is another interesting thing of why it is good to create these higher level functions, because maybe you you write it and solve it and make the whole program with 4, and then you realize, oh, then there is a better way. I can actually do it with 3 queries, and you just change path, and everywhere in the program automatically benefits from that. So how can you do it with 3 queries? Well, basically you can use a very similar method, but instead of checking it like this, we can compute the LCA of A and B, and then if X is the LCA by itself, then that's it. We have solved it. We can already say that it is in the path because the LCA of A and B is always in the path from A to B. But if not, then what we can ask is instead of OR here, we can basically ask for a XOR condition. We want X to be an ancestor of A, either of A or B, but not both. And that not both part immediately takes care of disallowing it to be here. So the only thing that remains will be the main path. We have to check separately for the LCA, and that's why we need 3 queries and not only 2, because the LCA is the exception. It's the only node that will actually be an ancestor of both, but is part of the path, and we would like to count it. But that way we can do it in 3 queries, which is interesting. And I hope this example, if you've never done interactive problems before, I hope that this example I'm showing you makes you think how interesting they can be. And they feel like a mix of math problems and data structure problems somehow. I don't know, I like them a lot. I think they are very interesting problems. A related query we might want to solve is also using the LCA as a basic query given by the problem, is what is the LCA of A and B, but with respect to root R. So we would like to specify any node as a root. So let me clarify this. In the problem, there will be a root with there will be a tree with a certain root, which we don't know, or maybe we know, I don't know, but the thing is that we don't actually know the tree. We can only ask LCA queries. And LCA is defined with respect to that root. But I want to ask queries of the LCA of 2 nodes with respect to any root. So for example, I don't know, if I take these 2 nodes, the LCA normally, and the one that the problem will answer me if I ask, is this node over here. But if I took instead this node as the root, then the LCA would actually have been this one, because that is where the paths towards the root for these 2 nodes meet. So the LCA, what node is the LCA can actually change depending on the root, and I want to implement precisely that. So how can we do that? Well, basically we can first ask for the LCA of A and B, and that will give us the normal, let's say, LCA with respect to the original root that the problem actually uses. So let's say this one is the LCA. This is the one that the problem will answer us, and let's call it Z, just because. But there might be more tree up here. Well, then we can make a check, and if our root, our intended root, is actually here or here or here, or actually anywhere in the tree above, let's say, or maybe not above, maybe it can be like a cousin far away here, but it has to go that way. Then if this one is the actual root, then the normal LCA will also work, because the path from these 2 nodes to the intended root has to go up into this one anyway, so it will still be the LCA. So we can make that check, which is basically checking if R is a descendant of Z, and if not, if R is not a descendant of Z, that means it's not in this subtree, then we're done. This is the correct answer, and that's fine, we're done. Otherwise, if not, then R will be somewhere within this subtree. I don't know, it might be here in the path R, or maybe it's somewhere around here, but it is inside the subtree. So so then we can ask for LCAs of R with A and LCA of R with B. And what you can convince yourself of by looking at the drawing is that in this case, exactly one, well, not necessarily exactly one, but one of these two will be equal to Z. Because, well, if R is exactly Z, then then actually both of them will be Z. Otherwise, since it is in the subtree, we're analyzing that case, Z will be, let's say, to the right, anywhere, maybe it's outside here. Then the other LCA, the one between R and A, will actually be Z, because you have to meet here. And reciprocally, if R is located towards the left in this drawing, it will have to, the LCA of R and B will be Z. And if it is somewhere else through another branch, well, actually both of them will be Z. But in any case, one of them is always Z. And you can actually check in those same cases that the actual LCA that we are looking is the other one, the remaining one. So for example, in this drawing, the LCA between A and B with respect to R would actually be this node over here. I don't know, X. This is the answer. Because this is where the paths going from B to R and from A to R meet. But that path is actually the LCA between R and A. And the other one, LCA RB, is the one that is Z. So we can always answer the one that is not Z. And if both are Z, the answer is also Z. And that can be written very nicely, very compactly by just saying, well, it's the sum minus Z. The sum is not important. We could also use the XOR actually, because we know one of these will be Z, and we would just want to say, well, the other one. And so this way we can solve it. And if we check, we have also used 4 queries like before. We have to do one LCA to compute Z. We have to do this check to see if R is a descendant or not, because if it is, we know it is in the subtree, and we proceed. But if it's not, then we've finished. The answer is Z. And otherwise, we take this as the answer. And we can also, like before, improve this to only 3 queries by noticing that we can just ask LCA AB and LCA RA and LCA RB, which is nice because those 3 are actually the LCAs, the pairwise LCAs between our 3 inputs. So that's very nice. Because having those 3, we can actually check and deduce whether R is a descendant or not. So we don't actually have to query. We can deduce it from the other values. And that is basically because this property that one of these 2 will be Z holds exactly when R is a descendant. So it can be used as a way to determine the value of this query without doing it and getting to 3. Because if R is somewhere else in the tree but not in the subtree, then we can actually see that that the place where well, this node will not be an ancestor of R. So in these LCAs, whose answer will be an ancestor of R, it will have an ancestor further up than Z. So definitely the answer will not be Z here and will not be Z here, and we can use that to detect, oh, it is this case. So the final answer for the original query is Z. Okay, let's continue now with another idea, which is very useful, and I call it the information theoretic heuristic, which is an invented name, but we'll see why I call it that way. It's actually a pretty simple idea, but very useful. So let's suppose that we have a problem where we have to discover a secret, and the secret is a hidden number between 1 and 1000, say. So there are 1,000 possible numbers, but we don't know which is the secret one. So we might model the state of the program and the decision-making progress sort of like a tree, where we start at the root node at the beginning, and there are 1,000, that's why I write 1,000 here, possible results to consider. Now, the evolution of this tree will depend on which questions we choose for our program. And of course, there will only be some queries allowed by the problem statement. For example, let's suppose that we ask, is the number lower than 10 or lower or equal to 10? Well, there are two possible answers, yes or no. Now, how many possible consistent results with all the questions that we've asked so far do we get? Well, if the answer was yes, we will know that the number is from 1 to 10, so there will be 10 valid results. And if the answer is no, then all the other results are possible, which are 990. And maybe one could continue asking questions. So, for example, if here we ask if the number greater than 10, then a yes answer would give us, I don't know, like 980 results, and a no answer would leave us with only, is this correct? No, this is not correct, because this question asks the same as before. So I already know here in this possibility that the 990 possible numbers, if I write the set, is actually 11, 12, etc. I know that it is more than 10 because I was answered no to this question. So when I ask greater than 10, actually, if I classify these results and consider which ones give a yes answer and which ones give a no, then if I ask now, is it greater than 10? All of them will give a yes. So actually, I will get to here with 990 results. And well, a no would be an interesting outcome because there would be 0 consistent results. So if the checker answers no, it means that it is wrong. It's a wrong checker. So this won't happen. So this question is actually not useful at all. But okay, maybe I wanted to ask. Okay, 1,000. Maybe I actually wanted to ask, is it greater than 990? Let's say. So now, yes. If the answer is a no, we come here, and if the answer is a yes, it's the other way around. There are only 10 possible results because I know the number is from 991 to 1,000. Okay, and so on. One can model the process as a tree. And of course, if I choose different questions for the algorithm, I will get a different tree. So basically, a concrete execution of the algorithm maps to a precise tree. Let's say that if I had asked instead, let me show an example. If I had asked instead, what's the number mod 3? Maybe the question, the problem allows me to ask that. Well, then all my numbers are classified depending on the answer, and the answer can be 1, 0, 1, or 2. Now, if the judge answers 0, there are three possible results, I think. If it's 1, it's 3, 3, 4, because 1,000 is 1 mod 3 and 3, 3, 3. So this would be the start of a tree if the first question asked by the program is what's the number mod 3, and it gives a different tree, and so on. Of course, actually, I am writing the numbers here only, and that means how many results are still possible given that we are here in this node. But actually, like I wrote here before, here all the actual set of possible results is from 11 to 1,000. Here the set of possible results, for example, if it says 2, will be 2, 5, 8, and so on. So each of these nodes is attached to an actual set an actual precise set of all the possible results, all the possible values of the secret that I am trying to find that are still consistent with the answers. Well, etc. The tree will depend on the actual questions that I ask, and where to which children in this tree that I am building we will move in an actual execution of the tree. That will depend on the answer of the judge. Now, the information theoretic heuristic, as I call it, and I will expand a bit on why I call it like that, information theoretic, is basically the idea that you should try to split as evenly as possible. You should try to use queries that split as evenly as possible. For example, well, something that we really know from binary search, if you can ask if the number is lower than something, you should not ask something on the board that's like here, 10 is too close to the minimum. You should ask something in the middle. If instead I had asked, is the number lower or equal to, let's say, 500, then I will have to have two answers, yes or no, but they would both be 500. They would both have 500 possible results. And intuitively, we know that this is a better question than this one. How can we quantify so? Well, the idea behind this heuristic is, well, to try to use as few questions as possible. You should first consider all the possible queries that you can do at any stage in the algorithm. Consider all the possible queries that you can do, and for it, and consider these children nodes that question will generate, and then going back to the idea that this is a two-player game, if the checker is adaptive, and that could be the worst case, the checker knows actually this could be an implementation of a pretty evil adaptive checker. You actually keep these sets and these sizes, and you keep track of what answers are still consistent, but you still don't choose anyone from the set. You just keep the set of all that are consistent. And then, based on the question that the contestant asks, you as a checker would consider the new set that will be created depending on what you answer. And then you will choose the answer that leads to the larger set, because that will discard as few, that's like the unlucky answer, basically. That will discard as few results as possible. The idea of the contestant is, of course, to reach to a node with a set of size 1, let's say 37 or 42, the magic number, the number of the universe. That is the idea, to get to a 1. So the contestant wants to reduce the sizes of the sets of valid possibilities. So the checker should answer trying to leave large sets. So if we assume that, and if we assume that the checker is even and will always answer the one that leaves the larger set, then of course, if we want to reduce as much as possible in a single step, the optimal thing to do is to choose whichever query we are allowed to do, such that the maximum value of a child, I mean the maximum size of the set of possibilities for a child node from the current node, wherever we are in the algorithm, is minimized. So again, we want to minimize the maximum value, the maximum size of a child. Now, since the child will actually be disjoint, basically, because at least unless these questions that I am asking have a probabilistic answer in nature, and unless there is a probability, which might happen in some problems, especially Gaussian problems like to add probabilistic stuff like this. But unless there is some probability that the checker will lie or something, then if the answer is correct and is well defined like this, each different answer will lead to different results, because for each result there is only one, and exactly one possible answer where it fits. So this will always be a partition of the further results. Eventually, if the question is very bad, it might happen that the partition puts everything into the same set, but okay, it's always a partition. So we want to choose the question that has the largest of these children sizes as small as possible. And that typically means, logically, that we are trying to split as much as possible. And also, as you can see here, if you have an option of a question that is not binary, whose answer is not only yes, no, but actually has many values, and you manage to make a question that evenly splits the space of possible solutions among all those different values, that's like perfect. That's like the best questions you can actually do. Now, when I say the best, I should emphasize that, that's why I say heuristic here. This is in no way optimal, actually. If you want the optimal worst case number of questions that you have to ask in general, in principle, well, you probably should treat this like a two-player game. And you might have to actually create the full tree of possibilities, considering all the possible questions that you can make and considering all the possible answers that the judge can do, and then run a minimax algorithm to compute the optimal value. So every time the judge has a choice, it chooses the answer that maximizes the total number of questions based on recursively what happens in the next subtree. So that would require, of course, to explore a tree of possibilities that is normally huge, but in some problems it might not be huge, and it might be possible to actually brute force or compute it exhaustively. But this particular heuristic is based on a single step and not looking at the whole tree. So it's not generally optimal. It's sometimes optimal. For example, you can actually check that many times the heuristic manages to create something that is optimal. For example, if the only question is the number lower than a certain value, this heuristic, when repeatedly applied, always splits in the middle, and thus it creates binary search. It magically turns into binary search, which is the best you can do against an evil adversary. Well, it will always choose the largest one, so the fastest way to get to that desired one result is to split evenly. So, yeah, this is basically the idea of the information theoretic heuristic, especially for IOI. Of those of you who are preparing for IOI, this heuristic can be useful to get approximate or subtasks at least, because maybe you don't do the optimal number of questions, but if you actually choose from all the possible queries the one that splits evenly, very often you will get very good solutions. For example, I remember a problem from a past IOI which just applying the heuristic as I told it, at each step choose from all the possible queries and choose the one that minimizes the largest child, assuming that the opponent chooses in an evil way. That got like 70 points from 100. So that's quite nice. For those who know IOI, getting 70 of 100 score for a problem is typically a very good score. Even though it wasn't optimal in that case. But also this heuristic can help us shape our mind and try to find what would be good queries. Because, for example, if our problem has some operator like this one, where you can ask mod or mod 10 or actually anything that has many possible outcomes, and we then by using this heuristic we can check that if we are actually using it in such a way that only 2 of those possible outcomes are populated, so that we are using it actually as a yes/no question. Well, this gets you to think, this is probably a bad question. I should try. I don't know the shape of the algorithm yet, but while thinking, you can say, okay, I should try to think about how to possibly use queries that actually split into different results, because sometimes it's not obvious how to then continue asking and use that, but at least you know, okay, to get better results, I should try to use that. And we can quantify this because actually, assuming, let's suppose that there are k possible answers to the judge, to the questions that you ask by the judge. So, for example, if the questions are yes, no, which is a very common case, k equals 2. There are 2 possible answers from the judge for each query. But I don't know, if the answer is the number mod 10, so to say, the k would be 10, etc. Okay, if you know the number of questions, that basically tell you into how many children you will branch, and optimally you would branch into children of equal size. So basically you can divide by k each time, assuming you manage to make excellent queries that perfectly divide. You will be dividing by k at each step. So how many steps do you need? Well, by this semi-logic, we would need, if we have n possible results, so n was 1000 in our examples, if at the start we have n possible results, we would need that n, once I've divided by k t times, if I will do t steps, must go below or equal to 1, because we want to get to that, remember, we want to get to that special, to a node where the set of possibilities is just one single number, and that will be the secret. Then I can answer. And so by rearranging this, you can basically get to the idea that, to the idea that t must be at the very least, because we're assuming the optimal case that we split perfectly, t must be at the very least the logarithm of n to base k, which is the same as log n divided by log k. I will generally use log like this to mean logarithm base 2, but here, of course, any base will gives the same result. That's it. So this is why having larger values of k is better. That leads to less queries. So yeah, this is the basic form of the information theoretic heuristic, but I haven't explained why it's called like that. Why I call it information theoretic? Well, the idea comes from information theory, basically, and it could be useful in problems that have probabilities. I imagine this possibly being useful in a Google code jam if the problem specifies some probability distribution that is not uniform or something like that. Well, then it might be useful, but it's not common to use the full information theoretic idea. Just this basic try to split evenly. But in information theory, there is something called entropy. And when you have the set of possibilities, 1, 2, 3, etc., let's say that each possibility I has a certain probability, p sub I. So, for example, maybe because of the problem, I know that it is not evenly distributed. The judge will choose the secrets at random, but there is a certain distribution. Not all are the same. Then, information theory defines the entropy as the sum of the probabilities times the log of 1 over p. Now, this is the entropy, and the entropy is basically how much information, that is why this is called information theory, it tries to quantify information, how much information we have to extract in order to reveal the secret. And this is on average, because information is basically a probabilistic concept. It has to do, information inherently has to do with probabilities and chance. So this is measured actually in bits, if the log is base 2. So what would happen if all the PIs were 1 over n? Because they are all equally likely. Then if we make the calculation, this would be the sum of 1 over n times the log of the inverse probability, and that is n. Since there are n values, this sum is just log n. And of course, how many bits? I told you this was measured in bits. So how many bits of information do you need to encode one possible result among n? Well, of course, the logarithm. So it makes sense that we need to find out log n bits of information. For example, if n was 1024, Well, there is a secret that we don't know among 1024 values. So how many bits of information do we need to discover? Well, of course, 10 bits, because that number can be encoded in 10 bits. But this is a general probabilistic definition that works fine. So for example, if this says 7.3 bits, then okay, we need to discover 7.3 bits, even if that's hard to imagine. Well, why is this useful? Because actually this information measure appears in many inequalities. Basically, in the same way as I've calculated how much information we need to discover, you could compute by the same formula how much information you're gaining in a certain question. Of course, that's on average, because it depends on the probabilities. So this expanded analysis will be useful in a problem that has some probability distribution specified. In that case, when you have a certain probability distribution, you can compute the entropy of one single step of deciding, and that will give you how much information you gain on average. The way to compute it is the same. You have your initial results in this particular node that you're considering, and you have all the possible results, and each of these will have a certain probability, however they are. This probability of how likely it is that the answer that you will get will bring you here, of course, will now depend on the probability distribution. But once you have those probabilities, you can actually compute the same value for one step of the question and compute how much information this entails. And that will be the same, the sum of the probabilities times their inverse logs. And this will tell you how much information you gain on average for that question. So in this case, the information theoretic heuristic would be to compute this for all possible questions and simply make the question that gains the most on average. And also using this and knowing how much information you have to get in total, you can get an estimate or an expected number of questions that you must ask. Or at least you can get estimations about it. For example, you can get an estimation of how much information will I get on average after n questions. So notice that when all the probabilities are the same, so it is equally likely, we know that the information gain is logged the number of results, which we were calling k. So in that case of equal probability, if we are gaining log k bits of information per question, and we need to reach, remember, we needed to reach a total of, the total initial entropy, which we know is log n when they are equally likely, then intuitively you would expect that we would need something like log n divided by log k, because this is the number of bits of information that you gain per question, and this is the total number of bits that we must get. And we had already computed, we had already computed that is the minimum possible that you have to do against an evil adversary. In the case of an evil adversary, it is an adaptive checker. I mean, it is even worse because there are no probabilities. The checker will choose the worst option. And we had an argument, a solid argument without probability that in that case, no matter what we do, we cannot get below this number. This number is the absolute minimum questions we have to do. So it is very nice to see it actually pop up here very naturally when we intuitively try to make an estimation of, how many questions will I need if I use this heuristic and I manage to split evenly, and there is actually an equal probability of results, or results are equally likely. We get to the same number, which is interesting. One final thing, the maximum entropy among all possible probability distributions is actually the equal probability distribution. So when all the n results are equally likely, that's the maximum possible entropy. and we know that in that case it's log n. We've computed it, so the entropy will always be at most log n. That means that if we know a more particular probability distribution, we might be able to lower the number of questions that we have to do on average by asking skewed questions, by asking questions that do not split evenly. Maybe the best way to split is different, because that increases the information gain, and the exact computation is this one. But still, this is still a heuristic. The absolute optimal case would require computing a full game tree and choosing making minimax algorithm and choosing the optimal game tree solution. But that is usually intractable and impossible. But this heuristic gives very good results. So I wanted to share it with you, and especially even these basic ideas of the heuristic, even if you don't ever use it to compute specific values, can help you guide the intuition of which questions to ask in order to try to gain as much information as possible. And also, this bound is very useful because it sets expectations immediately. You know that this is absolutely impossible to lower against an evil opponent that chooses in the worst case. I mean, it is impossible to make an algorithm that in the worst case makes less than this number of questions. So that can inform how good an algorithm you can get, because very often you will see that interactive problems give you a number of questions that is slightly above this theoretical number, and that already tells you, okay, I cannot waste too many questions. I have to make questions that are almost always close to this idea of perfectly splitting, because otherwise I won't get to this number. Also, one final remark, this is the idea behind that famous demonstration, that famous proof that actually you cannot sort in less than n log n comparisons, because actually when you have a comparison-based sort, you have k equals 2. You have only yes, no question, or maybe you have k equals 3 because you have lower, equal, or greater, but it doesn't matter. Basically, you have a constant number of results. K will be a constant number. And so, by our bound, since there are n factorial possible outputs, because our secret is what is the permutation. The secret permutation is what we are trying to find. And there are n factorial possible permutations. So in that case, this bound becomes log n factorial divided by log of 2 or 3. It is a constant. So any algorithm, any comparison-based sort will, by this same argument, require at the very least log of n factorial comparisons. And well, if you make this calculation carefully, this is on the order of n log n. So apart from a constant, this is n log n, and that is the reason. Now, I want to show you an example of a real problem from the IOI 2016 practice problems. It's called Martian DNA, and basically it's about discovering a secret. So it's just like the examples of ideas we've been doing. The secret, what is the secret? The secret is a string of length 1,000, a binary string of length 1,000. So 1,000 binary digits. And we have at most 1,020 queries. And the queries are yes-no queries. And what the only thing that we can ask in order to discover S is substring, is S prime a substring of S? So we can choose another string, S prime, and the system will tell us yes or no whether that is a substring of the hidden string. And that's all. And we have at most 120 questions, and we must discover the hidden string. So this would be the function, just to encoding our queries, just to make it clear. We pass it as a string, any string we want, and we are told if that is a substring of the secret or not. So well, the first thing we can do is to estimate based on the heuristics, to have an idea of how much we must discover per query. And we can find out a lot just by doing that, because, well, the space of all possible strings is 2 to the 1,000. So the logarithm is 1000, which obviously another way to say is that there are 1000 bits of information hidden, because we need 1000 bits to encode a binary string of 1000 digits. And we are given only 1020 queries. They are binary queries, so they give us at most 1 bit of information per query. So we're only given slightly more than the theoretically optimum that we know. So we know that there is no algorithm in the world that in the worst case is guaranteed less than 1000. This is impossible. No way. So the optimal is 1000 or more, and we are asked for 1020, so we don't have too much margin. Basically, by this calculation, we know that on average, we have to discover 1 bit of information, so 1 digit of information per query. Maybe slightly less, but we cannot discover half a digit of information, half a bit of information per query. That would be too slow. It would require 2000 queries. So already this gives us a very nice idea of how will the algorithm look. Well, the algorithm will have to probably discover 1 digit per query, because if it's discovering much less, that's not enough. So how can we discover 1 digit per query? Well, we might try to grow the string that we know 1 digit at a time, and that is basically the main idea. So we might start by asking, hey, is 0 a substring? And if we are incredibly lucky and the answer is, let's say the answer is no, 0 is not a substring, then we're finished, because we know that the answer is all ones. So maybe this is not a great question to start, but don't worry. Let's just imagine that we do it. So yeah, now we know for sure that 0 is a substring. So this is definitely a substring of the original. But we might ask, what happens to 0, 0 or 0, 1? Probably one of those will be, but we don't know which one. So maybe we ask, okay, what about 0, 0? And we ask again with 0, 0. Is that a substring? If they tell us that it is, then great. We will already know 2 bits. We know that it has 0, 0. But well, we don't really have 2 bits full of information, because we don't know where those 0, 0 are, but more or less we're getting close. So yeah, we know that, and great. But what happens if it tells us no, 0, 0 is not a substring? Well, since we know that 0 is a substring and 0, 0 is not, well, we will assume that 0, 1 is, because that is the other case. Notice that it would be actually very easy to solve this problem with 2000 queries, but we are not allowed to use that many, because we can make 2 questions. We can basically make 0, 0 or 0, 1 just to check, and if one of those returns true, we've managed to grow the string by 1. And if both return false, we know that we're at the end of the string, and then we can do the same backwards. So, well, maybe 2002 questions, but something like that. But we need to do better. So here, in order to avoid making 2 questions per digit, we have to do about 1. We will ask for some number, for example 0, and if we get a no, we will assume that it's the other one. Then we continue like that. Okay, maybe I now ask 1 just because, and they tell me no. Okay, I will assume it's a 0. Then I ask, okay, give me a 0. And if they tell me yes, then I'm lucky, because I asked 0, 1, 0, 0, and they told me yes. So it doesn't matter that I was guessing in the middle. It seems that I guessed correctly, and now I can say, okay, I am completely sure, because I got a yes, that this is part of the string. I can just go on with this very simple idea. I can ask 0 or I can ask 1, it doesn't matter. But the thing is that if I get a yes, cool, I guessed, and if I get a no, well, I assume that it was the other option. And of course it could fail, because for example I could get 1, 0, 1 and I get a yes, let's say, and then I start guessing whatever, and I always get no's. So I start adding things, but I get for example, I asked 0 and got no, so I put a 1. I asked 1 and got no, so I put a 0, etc. But actually the true string maybe is like 1 1 1 1 1 1. Yeah, like that, let's suppose. All ones and then 1 0 1. So I am always getting no matter what I put, basically because there is nothing. This is the only place that 1 0 1 appears at the very end, and so any string starting with 1 0 1 and then anything else will always be a no. So actually all that I'm getting are always no's, but not because I was choosing the wrong digit, just because I was already at the end and I don't realize about it. So how to fix it? Well, there is a probabilistic solution to this matter, which is okay. For example, let's keep doing this 16 times, at most 16 times. If at any point I get a yes, actually, well, this resets, because like I said before, if I was doing all this and get no, but then I ask 0, let's say, and I get yes, then everything suddenly changes, because this was not part of the example. I just asked about all of this S prime, and I got a yes. So it's like I can reset. I am completely sure that this is part of the string, and I didn't waste anything. So I can take it as my base, so to speak. But what if I am getting, let's say this was the last time that I got a yes. I asked about this string, and this was the last time that okay, let's keep that. The last time that I got a yes was about this string, and now I am asking about this one. Sorry, the opposite. I am asking 1 0 1 0, and I get no. I assume I won, so I ask 1 0 1 1 1, and I get a no, so I assume a 0. I ask 1 0 1 1 0 0, and I get a no, so I assume a 1, and so on. So I am getting a lot of no's up to this point. And let's say that I get 16 no's in a row. Then I say, oh, 16 no's in a row. And that cannot be, because if I am choosing, and here's the trick of the probability solution, if I am choosing at random, not always 0, for example, but random, I am randomly choosing what to guess. And if I get a yes, cool. But if I get a no, I take the other one. But I am flipping a coin and asking that question, the question that the coin gets, then no matter what the string is, actually, I always have 1/2 a chance of guessing. Because if it was a 1 or a 0, it doesn't matter, because I am throwing a coin. So there's a 1/2 chance that I hit it. So the chance of failing 16 times in a row is 1 divided by 2 to the 16. This is not incredibly unimaginable, like winning the lottery. Winning the lottery is much harder than this, but it's quite unlikely. So I might accept this probability and say, okay, this is my chances of failing. So what I will do is I will assume that if I get 16 no's in a row, no, I wasn't unlucky. It is simply that somewhere along the way there was the ending of the string, and that is why I'm getting so many no's. Actually, I don't know where on the string I am getting that many no's, because maybe it is here, maybe it is here, maybe it is here. I am not completely sure of where on the string I am getting the end. So, for example, maybe the string actually continues 1 0 1 1 0 1, but then here it ends. So these first 3 no's I got because I was guessing 0 1 0, and I was guessing wrong 3 times. But then I got all the other no's because I was at the end, and so I cannot continue. So in order to know where exactly the string ends, I can do a binary search, and since these are 16 positions, I can do binary search with just 4 questions, because 4 is the log of 16. So 4 plus 16, I did 20 extra questions in this case. But after that binary search here, of course, in the binary search, I would take the middle and say, well, okay, was the string actually 1 0 1 1 0 1 1, let's say. And if I get a no, then I know, oh, okay, the ending was before, because I was already failing. If I get a yes, then all of this exists, and those the cut has to be on the right. So that way I can do binary search. So with these 20 questions, I can get to where the actual ending is. Let's say I find it here, but on the worst case, I will find it here, so I will have no extra digits at all. But it doesn't matter because the wasted, so to speak, question that I've used are only 20, which is exactly the bonus that I have allowed above the basic 1000 that would be the ideal get 1 bit per question. Now, once I know that this is the end and I don't know that this string actually appears, I just keep doing the same on the left. Because now I know that this string does not appear any other place before. Otherwise, I would have managed to get a yes somewhere else. And so what? Oh, so I can continue. If I know that this is S prime and I know that it appears here, well, then I ask, is 0 S prime as of string? If I get a yes, great, I've grown 1 to the left. And if I get a no, then now I know that it must be 1 S prime. Because the ending cannot be here, because I know that the ending is on the right. And, well, I have to get to size n. So this is a cool probabilistic solution, but of course, I am assuming that there was some string fixed beforehand. It doesn't matter which one, because since I flip the coin myself, no matter how evil the problem setter is in choosing which string to use, it's the same to me. The only thing that matters is that it is some string fixed previously, and that it doesn't change mystically while it is running. But of course, if the checker is actually adaptive, remember this is a two-player game. The checker is an opponent and is playing against me. If the checker is actually a program and doesn't have to actually fix beforehand the string, then this solution can be made to fail by a smart test case, so to speak. In interactive problems, the test cases are actually programs because they are opponents, and your programs might be run against different adaptive programs designed to make different solutions fail, possibly. This is why it is very hard to make good test cases for interactive problems if you accept adaptive programs often, because often it is not super obvious how to make the worst enemy. That's adaptive problems. Sometimes there are very good things to do, like the information theoretic heuristic using reverse. You answer the question in such a way that the least information is given, but otherwise it's very hard. But here, for example, an enemy program would actually answer yes a few times and then decide, okay, now I will start answering no, 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 and then I get no, 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 and here I assume oh, it must be that I was unlucky. No, sorry, I crossed the ending. I cannot be that unlucky. So I will start making the binary, and there the adaptive program may detect, oh, he's asking again about shorter strings. So now I will start answering yes, 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 yes. And so the binary will say yes, 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 and it will get, oh, I was correct everywhere. So actually, maybe this was not the ending. Maybe this was just that I was incredibly unlucky. And of course, you were not really incredibly unlucky, but the opponent is making sure that you are unlucky. It is changing the string dynamically based on your question, so that you're always on the worst case. And this would make you fail, or fail either because you answer the wrong string, or fail because you make too many questions. So yeah, this is a problem. And this problem can be solved even in the presence of an adaptive checker by a slight modification. It is the same basic idea, but we have to try to... the idea here is like getting to a string that cannot possibly be part of the main string. Because then we know, okay, this is impossible, this cannot be part of the main string, and so I can do binary search and look where is the cat that determines that the string ends here. In the probabilistic one, we get sure that we get to a string that cannot possibly be there, because the argument is that we are flipping randomly, and so if we get that many no's, the chance that the opposite string is actually there is very low. So probably what's happened is that we crossed. But we can get to a similar conclusion deterministically in the following way. First, we make a binary search to find how many zeros appear consecutively at most. That is easy. For example, we ask first 500 zeros, and if we get a no, there are no 500 zeros consecutively. If we get a yes, there are. And so with 10 questions, because that's the log of 1000, we can get the maximum number of zeros that we get a yes. Of course, if we get all no's, the string is all ones, so very easy. So we got this number, and we know that this appears. And this is the maximum number of zeros that appear. So then what we will do is that we will start asking for more zeros. Of course, if we ask one more zero, we will get no answer. So we will assume that it's a 1. So that's... in reverse. We will ask for a 1. So of course, here we might get a yes or we might get a no. If we get a no, we are sort of lucky because we already know because of the binary search that it can't be a 0. And we have asked for a 1 and we got, there is not a 1 there as an answer, so this must be the ending. But we might, if we get a yes, then okay, we know that this exists. And we always ask about a 1. Unlike before, whenever we get a yes, okay, we are lucky and we can reestablish our state saying, okay, this appears definitely because we have just gotten a yes, and so we continue happily, and we are getting 1 bit per question. The problem is if we start getting a lot of no's. That's the problematic case, just like before. Because just like before, we will always ask about a 1, and when we get a no, we will assume, okay, it must have been a 0. So we get no, we are putting zeros. If we happen to get a 1, we're super happy because when we get a yes answer, we know that that appears and those will reset. But what happens if we get no? Well, here, let's say k was the maximum number of zeros. When we get to k plus 1 zeros, we know that that cannot be. That is impossible because we had done the binary search first. So once that happens, it means that we have crossed somewhere here the true ending, and that is why we are getting no's. And so we can make a binary search just like before, and that will take at most 10 again. So there we find the final suffix, and then we start adding characters on the left just like before, but this one, since we know where the string ends, we know that this guesses will be correct. So basically, if you make the calculations, you pay 1000 because all of your queries are getting exactly 1 bit of the string, except for this extra of the binary search. And that's basically it. So you do at most 1020. Actually, you have to be slightly more careful with this calculation because all of these k plus 1 zeros that I did, or I think that those are k. I'm not sure. Yeah. Okay. All of these ones did not reveal me an extra character of the string, but it doesn't matter because all of these k zeros were actually free because I already received them because of the binary search. So that sort of compensates. Here I waste about k questions, but I had k free questions here because of the binary. So if you make the careful calculation, this is fine. You never go above the number if you do it right. So yeah, this is an actual example of a very interesting interactive problem. Now, I want to give you another example of an interactive problem, which I think was a very nice problem that we used for our national selection contest at Argentine National Olympiad in Informatics. It's a problem by Facundo Gutiérrez, and the name is Tyrannic. And this was like a parody of the actual Titanic. The Tyrannic is supposed to be a ship that was that sank on its first trip a long time ago, and we want to find it in the bottom of the ocean. So it's a parody of the Titanic. So what we know is that the search space is a grid of n times n squares, and the total area of the search space is at most 10 to a million. But we don't know the shape. It might be 1,000 times 1,000, so like a square grid. it depends on the test case. And in another test case, it might actually be 100 times, well, I don't know how much, 10,000. Okay. Anything that is at most 10 to the 6. And the tyrannic is actually a rectangle. So it was a very simple shape. A rectangle somewhere here. I don't know the shape, the orientation, nothing. Well, the shape is a rectangle, but I don't know if it is 1 times 100 or 2 times 50. I don't know. I know that the shape is just a rectangle. And to find it, we have some very special laser sensors. The thing is that we can basically choose any border of the grid, like here, or like here, or like here, from the bottom, from the left, from the top, but on the sides, and choose one border and say, okay, I will shoot the laser here. And what the system will answer is if it hits the tyrannic and how far it is. So if I shoot here, the laser will like go all through this, and the system will say no hit. The ship is not there. If I throw here, no hit. If I throw here, the system will say, oh, it was found at a distance of 2, because the laser goes and comes back and we can measure the distance. If we shoot here, the system says, okay, it found that distance once, and so. So our mission is to locate exactly where the tyrannic lies. That's basically it. I don't remember now if the ship has dimensions exactly 100. But let's say that we know that the tyrannic area, the area of the ship, is at least 100, because it's basically the same. There won't be an important difference. The ship has area at least 100, so that's good. We can use that for our problem, because basically, if the ship can be a single square, then we're out of luck. We basically cannot do anything better than shooting every single column or every single row, whichever is lower, until we find it. There's nothing better, basically. But we know that the ship has a certain minimum size, and that will allow us to do better. So, of course, we want to use as few queries as possible. For example, I just described one solution, which will take at most 1,000 queries, which is, well, a bit more, but let's see. We can shoot every row, for example, until we get a hit. We will eventually have a hit because the ship is there somewhere. And once we get a hit, we will know the left side of the ship. And so we can easily determine the right side by just shooting on the opposite side. And that will tell us the distance. And then to get the top and bottom, we can ask 2 more questions. One on the top, exactly to the right of this first hit that we got, like here, and this will tell us the top, and then one more that will tell us the bottom. I don't remember if we know the exact area of the ship. If we do, we might avoid the last question, because basically once we know these 3 sides, we can, based on the area, know where the last side is, but it's just one more question, so no, not a big deal. So with only 3 more questions, 3 more queries, once we have a hit, we can always solve the problem. So it is easy to see here that the critical part is hitting the ship. Once we have a hit, we know at least 1 square of the ship, and that is enough to, in just 3 more questions, completely determine the ship. But the problem is hitting it. So a simple way is shooting every row, and that will basically give us at most 1,001 question, 1,002, 1,003, something like that. Why 1,000? Well, because if the dimensions were actually, I don't know, 10 to the 5 times 10, like a lot of rows, then actually shoot the columns, because there are only 10 columns. So the worst case would be a square grid, where you have to shoot all of the rows or column, and it's the same, so 1,000. But we have to do much better, because the limit here for 100 points is 190 queries, so we have to do better than this. And that's where the idea that we know that the area of the ship is at least 100, because it was a really great ship at its time, so it couldn't be so small. We know that it was large, helps us do less queries. Because basically the idea is to shoot forming a grid every once in a while, and if we space the shots appropriately, we will be sure to hit the ship because it is large enough. So, for example, since let's say that the ship has area A times B. Well, either A or B, I mean horizontal and vertical, either A or B has to be at least 10. It cannot happen that they are both under 9, because otherwise it doesn't have enough area. So one of these has to be 10. And we cannot say the same for 11 because 10 by 10 is a valid size for the ship. But each dimension has to be, some of the dimensions has to be at least 10. So what we can do is basically, if this is the grid, we can shoot every 10 rows. So if I number them from 1, I do this is the 10 one, then I shoot at the number 20, etc. And I do the same with the rows. These were the columns. I do the same with the rows. I shoot at 10, I shoot at 20, etc. Now, it is easy to see because of this drawing that if we do this, well, first of all, the number of shots that I will do is the grid divided by 10 plus the other dimension divided by 10. So basically the sum of the dimensions divided by 10, because I showed 1 in every 10 rows. Now, if the ship has avoided all the shots, of course, if I hit the ship, I just do the final question and finish. If the ship has managed to avoid all the shots, it has to be somewhere in this middle part, because it cannot cross. And it is easy to see that these are all 9 by 9. So they have area 81 and are too small to contain the ship. So once we shoot at the very least the last one of this race, the ship has to be hit, because otherwise it would be smaller than it really is. And it is not hard to make an adaptive checker for this problem that actually forces you to do an optimal strategy like this, because basically the checker would always answer no, the ship is not there, and keep track of these portions and the sizes that they have, which can be done efficiently with a pair of sets in each dimension because they are independent, and only answer yes when answering no to the query would make all of the regions be too small to contain the ship. Basically, that way, if you don't do the questions very well, you won't get there in time. And also, this adaptive checker would answer would not care about where the ship is. It would, if you answer prematurely trying to guess, it would just say, oh, okay, no, you lost, because I know that the ship could be at least 2 different locations, so I will not even bother to decide which one it is. I know that it is still ambiguous, so you answering is wrong. So since the checker could be adaptive, we have to do it good. So this seems very good, because with this idea we've managed to do it in like the sum of the dimension divided by 10, well, maybe plus 3, but that plus 3 is fixed, not too much problem, just because of the final shots to narrow down where the ship is. But unfortunately, the sum of the dimensions could be very large. And we're not even there for the small case of 1,000 times 1,000. This would give us like 200 queries, so that's not enough. That's a problem. But we can do somewhat better, because we can see that with this grid, with this spacing of 10 every 10 rows and every 10 columns, these regions have size 9 by 9, which has area 81, which is smaller than 100, and that is why the ship cannot be there. But 81 is far away from 100, so we have a lot of margin still. Any size of these regions, which is smaller than 100, will do. So we might try to, of course, if we go for square regions, then 81 is the last square that is smaller than 100, so we cannot do better. But there is no reason to use square regions. Actually, it doesn't matter. In this argument, the only thing that matters is that the area of these regions is smaller than 100. So we might go for 99 in order to try to use larger regions here, which would imply a larger spacing and those less shots. So, well, 99 is 11 times 9, so that's nice, because then we can make these regions be 9 times 11. And so that means that in one dimension, we will still shoot every 10 rows, but on the other one, we will only shoot every 12 rows. And this one will be 24, etc. Because that way, in this dimension, it will be 11, and in the other one, it will be 9. So by the same argument, this will be 9 by 11 regions and will be too small to contain the ship. So when we calculate how many shots we've done, now it will be n divided by 12 plus m divided by 10, which is lower. Actually, we would, of course, like to choose n to be the largest dimension here in order to make less shots in total. And what does it give us? Well, that's great because for the case of a square grid, when we have 1,000 times 1,000, if we make the calculation, that will be 1,000 divided by 12 plus 1,000 divided by 10, which is like 183 if you do the calculation. Plus the 3 queries, we are below the 190. So great, we've solved it for square grids. But unfortunately, when we have very non-square grids, like 10 to the power of 5 times 10, something like this, well, we're very far from this number because even if we choose to divide this one by 12, that is already very far from 190. So we have no chance, basically, on a board like this. So now the rectangular boards are very bad for us because we're doing too many queries there. But the trick here is that this choice of 11 and 9 is still quite arbitrary. Like before, the only thing that matters is that this A, let's call 11A, one of the dimensions of the little rectangles that where the ship can finally be, and let's call B the other one. The only restriction that we have is that A times B has to be lower than 100. That's it. That's what we need. Well, of course, each of them must be at least 1. Otherwise, if one of those, if we wanted them to be 0, that would mean shooting every single column, and okay, we've already done that. That doesn't work. Any pair of numbers A, B that having a product less than 100 works, and the cost of choosing that pair A, B because of the same arguments would be n divided by A plus 1 plus m divided by B plus 1. So the thing is that we already checked that 11 and 9 is a great choice and it's good enough for square boards. But maybe in the case of a rectangular board, for example, in this case, when n was like 10 to the 5, n was 10 to the 5, but m was maybe just 10. Well, maybe in this case we wouldn't really care about this factor, m divided by b plus 1. If b is very low, let's say b equals 1, well, that doesn't matter because this will still be very cheap because m is just 10. What we care is that a is as great as possible. In this case, we could take a to be 99. That way, we would pay n divided by 100, which is just 1,000. And we might think, oh, that's really bad. Well, it's still not enough. But there's more. We actually already know that we have a solution with which does the minimum of nm shots. Basically, shoot every row or shoot every column. So in this very extreme board, we actually can solve it in just 10 shots. So basically, we're really interested in boards having both dimension, at the very least 180, something like that. And in that case, we can see that if we take an example like 180 and as large as possible, what we will see is that 11, 9 is not enough. But if you choose other values like these ones, you will get a different balancing of n and m, and you can actually get better solutions. So basically, that is the answer. That is the trick. you can first, knowing your values of n and m for this particular test case, brute force all the possible values of a and b, because basically you know that a and b are at most 100 each, so you can completely brute force it and check it, and compute for those whose products are less than 100. You can calculate how many queries you will do with this calculation. And then from all of those possible values of A and B, you just take the one that makes less queries and go and do it. If you do that, you can actually test it, and you will check that the worst case now is again the square grid. So 9 and 11 as fixed values do not work because they are not enough for unbalanced grids like 180 and a lot. Well, maybe not 180, but 200, so that we cannot do just shot every row, every column. 205,000, for example, should not be solvable by this, because if you take 11 and divide 5,000 divided by 12, this is not enough. This is more than 400, like 300, even more. So it doesn't get to 390. But if you choose other values of A and B, you can divide this 5,000 by a lot while still reducing this 200,000. Oh, sorry, we can actually use 1 and 99. Yeah, okay, because then we're divided by 2 and we will be dividing by 100. So we have 150 queries in total. So that is below our numbers. So yeah, basically by brute forcing which values of A and B you want to use, you can always find that the optimum always is below 190 queries. Now, last but not the least, I want to show you an example of another technique for which I have invented a name without too much sense, but I call it separating binary search. It is a binary search that separates things. It is used to separate the domain of a function into different parts. We will see what we mean. So there are cuts in the domain, and we will find those cuts. Okay, what is the context? The context is like this. We have a certain function over a domain. There are n possible values in the domain of the function. So yeah, you might think of this as an array or a list of n values, which are numbers that we don't actually know. And the numbers are from 1 to k. And the query is to actually reveal one of those values in the list. But of course, the abstract setting is that this is just a function taking values from 1 to n and taking its argument from the possible values from 1 to n. So that's the domain. And the function will take values from 1 to k. Basically, that's it. So this is a very general setting. Whenever there are n things in the problem, and for each of those n things, they could be up to from 1 to k of height, this will apply. It doesn't have to be an actual list that the problem describes as so. It might be much more abstract. But there's a property, and that is that f is a increasing function, or at least a monotonically non-decreasing function. So if I is lower than k, then the function cannot be the other way. So it might stay equal, but it doesn't decrease. It never decreases. That's the function. So what do we want to do? We basically want to know the full f. We want to reveal to ourselves the whole array. And I want to emphasize that n might be very large. So this, when I say array, this is like a metaphor. This list might actually don't even fit into memory. N might actually be like 10 to the 10. I don't know, 10 to the 20. It might be too large. But conceptually, this is the situation. There's a function over this domain that might be large. Well, we don't care about it. The thing is that we want to know the full function. And how do we know the full function? Well, the function, since it is monotonically increasing or non-decreasing, has at most k minus 1 cuts. It has k minus 1 places where it changes. now that I think about it, I think it's better to, I think it's better to, for the calculations, just to assume that it goes from 0 to k, so that the number of cuts is actually k. So there are k cuts in the function, because if we write its values, it will start with zeros, it then will have ones, it then will have twos, and so on, and when it has the first k, well, it will always be k, because k is the maximum possible value. So if you look, there is one cut here where it changes from 0 to 1. There is one cut here when it changes from 1 to 2, etc. And there will be one final cut where it changes from k minus 1 to k. Some of these might coincide. For example, if the function had changed from 1 to 2, instead of going from 1 to 2, it goes directly from 1 to 3, and there is no 2 in the values, we might think of that as actually both cuts coinciding here. So here we have both the cut that goes from 1 to 2 and the cut that goes from 2 to 3. We can think of that way. That way it is easier. So the function decomposes, the domain decomposes into consecutive intervals, but some of those, and they are always exactly k plus 1 intervals from 0 to k inclusive. That is why they are defined by k cut in between, because of course we know that the other borders are defined on the extremes of the domain. So we only have to find out k extra cuts, and it's easier to think that some of the intervals might be empty, and that will correspond to coinciding cuts. It's easier to think of it that way. So that's why I call it separating binary search. It will be like an extension, because actually this is a generalization of binary search. We will see it soon. That find the cuts, so it separates the values in the domain. And well, if I give you the k cuts, that's enough to actually compute any value of f. That completely determines f, because that tells you where the function changes, and that's enough. Basically, for any value of the domain, once you know the cuts, the value there will be the number of cuts that are to the left, because that's the number of times that we have done plus 1. That's basically it. So our objective is to compute where the cuts are. I said that this was a generalization of binary search, so this generalizes. Oops, here, believe me, here it says generalizes. You have to, you need to have faith. This generalizes binary search, the normal binary search. Why is this so? Because the normal binary search is exactly the case of k equals 2. We know that when we have a property that is binary, and thus we can do binary search, the property will be false, 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 up to some point where it's true, and then it will always be true. If it was swapping from false to true always, we couldn't do binary search. It has to be false up to a certain point and then always true. That way we can do binary search. And of course, if we change it to numbers instead of true or false, this will be 0, 0, 0, 0, and then 1. And we want to find where the cut is. That is the normal setting of binary search. This is the correct way to think about binary search. And well, of course, this is the specific case of k equals 2. So this is a generalization of binary search where there are more than one cut that we want to find. So yeah, I've seen this. I've seen exactly this situation in at least 3 interactive problems. So if you are going to competitions where there are interactive problems, this might be useful to know, because the thing is that the idea is to find the cuts with as few queries as possible. And so we will have to generalize binary search. And for the case of k equals 1, k equals 1, the normal binary search is optimal. It's basically what you want to do. But there are different ways to generalize it, and the most obvious way to generalize it will not be optimal. We will do quite more queries than necessary. Okay, so first of all, let's say that that we have to say first what happens if k is larger than n. So we have a lot of cuts. We have the possibility of having more cuts than the domain. When that happens, basically you have to evaluate everywhere, and you won't be able to do something significantly better than just evaluate everywhere. And that means that the number of queries, Q, is actually n. Yeah, just ask for the whole domain and that will be optimal. Intuitively, this makes sense. Okay, I mean, yeah, it's hard to think about something better. For example, let's say you have just 4 numbers and they are longs or something like that. K is huge. So it's very hard to do something smarter like that than asking for everyone. In fact, you can prove that you cannot beat asking everything. I don't know. You might think, oh, I'm very smart. I'll ask this one, because if I ask this one, they might say 0 and I gained almost nothing. But again, you ask for this one and they tell you, oh, it's 1000. Oh, okay. So the first one can be anything from 0 to 99999. And anything I ask on the right will tell me nothing about the first one, so I have to ask about the first one. Okay, I ask and I discover what it is. It doesn't change anything on the right. So now I ask for this one or for this one. It doesn't matter, but whatever they tell me, if I ask for this one, they might tell me 2000, and it tells me not enough about this one. It might be anything from 1000 to 2000, so I have to ask. And well, it is very clear with such an extreme example, but you can actually prove, if you want, that that you have to use n questions here, and the information theoretical bound might be useful to give you an idea about it, but it doesn't. It is not necessary. You can use a more elementary kind of proof, but it's very intuitive. If there are so many cats, then you have to evaluate everywhere. You cannot gain. The numbers are so huge and could be anything that you have to check them. But if k, so we will assume that k is lower than n. And for this to be actually quite useful and not just like gain one query, for it to gain many queries and be very useful, not gain only one, we will assume that that k is much lower than n. Or at least we will have that case in mind, because that's the most interesting case. Like, for example, k equals 1 is binary search, and there we only have to do log n queries. That's a huge boost. We would like to also have a huge boost for the case of k equals, I don't know, 10, 20, something small for a large n. Okay, enough talking. Let's think about how to solve this problem. Well, of course, n is the obvious solution. Ask everything, but we want to improve on that, assuming that k is low, because if k is larger than n, we can do nothing. So we will assume small k. What can we actually do? Well, the most basic solution would probably be, okay, I know binary search, and this is a generalization, so let's do many binary searches. And that's okay, that will work. It will not be optimal, but that will work. So you know that there are some zeros, then there are some ones, there are some twos, and we want to find the cats. And by definition, the first cat is you might identify with the index of the first cell. If you use the right cell to identify a cat, then the first cat is the index of the first cell that is larger or greater than 1. The second cat is the index of the first cell that is larger or equal than 2. The third cat is the index of the cell of the first cell that is equal or larger than 3, and so on. Each of those independently, if you treat them as completely independent problems, then what you have in each case is a binary property. You know that those numbers that are smaller than the cat, for example, this is the first cat, so 1, those numbers that are smaller than 1 will all be together at the beginning, and then after that we'll start the numbers that are greater or equal. So it is a binary property, and thus you can use binary search to find this cat. If you only wanted to find one single cat like this, then there is nothing better than you can do. If you're interested in just one cat and no more than one cat, for example, I want this specific cat, the first one, or I want the second one. It doesn't matter which, but if you want one specific cat, then doing binary search is the best, and you cannot improve on that. Log n is the optimal value to find one cat. If we treat each cat as something independent and do not use extra information from cat to cat, like for example, we call the function, okay, calculate the cat number 1, then calculate the cat number 2, then compute the cat number 3, and each is done completely independently, then we will have k times log n queries. That's it. If k is much smaller than n, then this should actually be an improvement. But it might be worse if k is smaller than n, but not so much. Yeah. For example, let's say that n is like 1,000,000, and k is like I don't know. No. Okay, 1,000. 1,000,000 is too much. Let's say that n is 1,000. And k is 100, so k is 10 times less than n, but nevertheless it will be the same because k log n is actually 10. Log n is actually 10 in this case, so basically each binary search will cost 10 queries, and we will need 100 binary searches, so we will do 100 queries in total. 100 times 10, and that is 1,000 queries. So we are not gaining in this case above the very basic algorithm. We would like to have something better. And in fact, we might be worse. If k is really large, this blind doing of binary searches might actually be worse, because it might be asking many times, at most log extra time, the same cells that we have already found in other binary searches. For example, in the extreme case of k equal 1,000, well, each binary search asks for 10 things, but across the 1,000 searches, maybe we've asked for like 10,000, and that is 10 times more than the full grid. Okay. How do we do better? Well, a very basic thing that you could do is actually to do each binary search not in the whole array, but taking as the beginning the previous cat. So you would do the first binary search and find the first cat like this. Then instead of doing the binary search in the whole array, you could actually start from this cat, so that you have a smaller domain to do binary. But that does not change the worst case. Unfortunately, the worst case is almost the same. It doesn't change. In fact, if all the cats were lumped here on the left, then the algorithm would always start from the beginning, and that would be bad too. You could add an if to check for that or something like that to make a slight optimization, but the principle is the same. If instead of being literally on the first position, they are all very close in the beginning with like random 1-2 spacing, well, it's hard to all of the binary search will be expensive, because in all of them the domain is large, so you're not gaining anything. We need to do something better. And an interesting idea here is that the problem here is the problem here is what happens when the cats are very close. When the cats are all lumped at the beginning, that is a bad case for this last idea. This was like an attempt, a very simple attempt to improve, where we said, okay, use the previous cat as a bound to search less, but unfortunately that reduces very little the space when the cats are very close together. But then, if the cats are very close together, what we can think of is, well, then it means that the first changes occur very rapid, very close to the beginning. So if n is say like 1,000,000, why do I have to, when I'm looking for the first cat, the first place that it changes, why did I have to look and do a binary search over the whole domain when only the beginning is interesting? And according to that idea, you might think, well, okay, let's do something. I will evaluate at position 1. Let's say I index the position from 1, like I wrote before. Then I will ask for the first one, then I'll ask for the second one, then for the fourth one, then for the eighth, and like that. So I am jumping by powers of 8. So I jump by let's say that my first jump is 1, then I jump 2, I jump 4, I jump 8. I am doing growing jumps. And I do that until I cross the cut. So for the first cut, I am actually looking at the array and seeing 0, 0, 0. And I do that until I see the first 1 or anything larger. If I see a 3, okay, I've crossed the cut, definitely, because I want to find the first non-zero. So once we do that, we have a range here that we know this one is a 0 and this one is not. So the cut is here or anything in between. But it's between these two. So now I do a normal, completely normal binary search just in this range. And then we found the first cut. And then for the next one, of course, if this is the first cut, then we do the same procedure, but starting from this cut that we've found. So remember, just to summarize, the procedure is like this. We have the cut from the previous iteration. For the first one, it's just the beginning of the array. And we start asking there. If we're lucky, we might see the cut right there. But if not, we'll start jumping. And we jump twice as long each time. Until we cross the jump. Or if we fall outside of the array, well, we take that as having found that there is a larger number here on the end. That we basically do that. Then we will eventually have crossed a jump. And find that the cut is between here and here, and then we do normal binary search. So with this, you will see that what you can check by doing the calculation is that basically, since we are duplicating each time in these jumps, if we call L the length between the last cut and the next cut, we will only have to do log L steps of jumping. After just about log L steps, we will definitely cross the cut. And then we will just need another log L steps because we will do a normal binary search. So basically, it will take 2 log L, where L is the distance between cuts, to go from one cut to the other. So the full complexity is the sum. It depends on the distribution of the cuts, but for any distribution, it's the sum. It's twice the sum of the logs of the different cuts. That is the number of queries, basically. And the constant is 2. That is accurate because you have to do this first stepping and then this extra binary search. This stepping is not optimal. We will later see the actual binary separating binary search, but this is a nice idea, and it works for other problems where you have to do this stepping. So it is a very good pattern to know. So this is tight. This 2 log L is tight, and well, the worst case now. You can check the logarithm function, and the worst case will be when the cuts are equally distributed now, because when you have a very long interval, well, that one is the log makes it be very efficient, basically. So you want it to be as equal as possible. So basically, you will have to solve k cuts. Each one will cost 2 log of n divided by k. Yeah, that's it. Because now the domain has a length of n. So when we divide it across the k cuts, it has n divided by k length. Yeah, I think it's correct. Yeah. Maybe this should be k plus 1. I think this should be k plus 1. But this is the general pattern. The most important thing is that there is this 2 here in the constant, definitely. So it's like 2 times k times the log of n divided by k, or maybe k plus 1 if you're careful. But this is the main shape. And when we compare it with the basic one, where do I have it? Oh, I erased it. But remember that just doing n independent binary search was n times k times log n. So this might be worse. It depends on the values, because we have 2 times k, so this 2 is pretty bad, times log n divided by k. So if k is small, such that log n and log n divided by k is not too different, this twice factor will make this improvement in the number of queries not be an improvement at all. But on the other hand, if k is large, for example, we had the case of 1000 and 100, k 100 and 1000, and in this case, this one does more or less 1000, so this was just like the basic check everything, there was no difference. But now this one is doing 2 times k 200 times the log of 10, which is like, how much is the log of 10? 4, let's say, 800. So it's gained something. And if n is very, very large, it depends on the ratios of n and k. How do we improve it? Okay, this idea of jumping is nice, is good. It changes the asymptotic complexity. I mean, asymptotically, this one has a 2, which in practice is quite expensive given the typical numbers that we have. But it improves the complexity in terms of k, because it puts divided by k here. So yeah, that's very nice. Can't we have the best of both worlds and have something like k times log n divided by k plus 1 eventually, but without that pesky 2 factor, so that we can say that this is definitely like the best in this case? Well, yes, and that is the idea of what I call separating binary search. And the idea is simply to implement a recursive procedure for this, where basically the idea is, like many times, try to split evenly. So you have this domain, and remember, in the special case of k equals 1, you wanted to do binary search, and the first step of binary search is to ask in the middle. So let's do just that, start by asking in the middle. Our previous algorithm did that implicitly, because we based the algorithm on doing binary search. It had an intermediate step that was called binary search, so there it would go in the middle. But now we do it explicitly. Let's always start by asking the middle of the range. And we will compute a recursive function. So let's say that we are computing f of a certain range, AB. So we know that we are between A and B. So this is the index of cell A, the first that is in our range, and this is the index of cell B. So our range is from A to B, like this. Oops. Like this, inclusive, exclusive. And what else? And we will know that the cut, that all the numbers in this range, all the numbers in this range that we are looking, which is the one that I marked here, all the numbers in the range are between, let's say, A and B. I will put it in green and in lowercase. So initially, the initial call is just, I want you to calculate everything. So go from 0 to n, or if we index from 1, this will be 1 n plus 1. Doesn't matter. Let's say it's from 0 to n minus 1, the domain. So 0, 1. And then the values. Well, we know that the values go from 0 to k plus 1. Those are the possible values according to the previous one. Because again, the range of values will be from A to B, inclusive, exclusive. This means that any value in this range, say it's x, will be A lower or equal x, lower or B. So this is like the invariant when we call f, and this is the initial call that we do to solve everything. I want you to compute the whole range, and you know that there the values are between 0 and k, so 0, k plus 1. So what do? Well, we define C, the index of the middle element, and we check C. So we call, well, I shouldn't call this f, so let's say binary search, because this is a binary search function. F has already been taken by the function. Now, as the first step, we compute f of C. And we know that f of C will be between 0 and k inclusive. We might, so in our intermediate step of this recursive algorithm, it will be between A and B. We in our implementation, we might actually put an assert here and check that actually we see a consistent value, that A is like this. And this is the value that we ask calling the interactive function to know. Because we know that if this is false, then the precondition of the function has failed. We've implemented the algorithm wrong somewhere. So, okay, we call in the middle. We see its value. Of course, it will be between A and B because that is our precondition. And initially, we call it with the full range and we know its value. So, what do we do now? Well, basically, we can check a few ifs. And there are basically two interesting cases. We will compute the left and the right sub-ranges completely independently. Because like in the little example of 4 cells that I did before, once you've asked here, here, and here, you can see that basically what's in the middle is like a completely independent problem, and getting values on the left or on the right will not affect the calculation of this range. Because in this range, since you've asked here, and assuming you've never asked in the middle, you know that all the values are greater or equal to the value fc, and lower or equal than, well, whatever you already knew before that they would be lower. That hasn't changed. And you don't know anything else, and any question outside of the range will not change that information. So you can solve each half independently. But there is even more. There is a trick. Like I said before, for the left half, you know that you would like to call binary search of A to C, and the lower bound is the same as before, but now you know that the values are at most fc, so you will put fc plus 1. Depending on the implementation, maybe it is easier to use inclusive for this one, but it is typically better for the range itself to use inclusive-exclusive, because that way you can just pass A and C directly, and that excludes C, which is what you want, because you don't want to ask about C. You've already done that. But it's fine. It's just taking care of the indices. You will call this, and you will also call binary search of C plus 1, because now we have to exclude C. B, and now you will know that they will be at least fc, and at most, what you already know, they were at most little b. So you do these two calls, but what happens initially on the first calls, A and B are not the same, because you will call with 0 and k plus 1. But in intermediate calls, depending on what you get as the values, eventually these values are getting closer and closer, and so you might end up with A equaling B. That might happen. For example, let's say that initially this, you know that your values are between 0 and 10, and you ask here and you get a 7. Okay, now you go to the problem on the left, you recursively end up here because of this call. You ask in the middle and you get another 7. Then you recursively call the right, and when you call the right, you will be calling a problem from here to here, and little a will be 7, and little b will also be 7. No, sorry, 8, because of our convention. But that means that the values here are between 7 and 7. They must be 7. That's the conclusion. So as a base case, you can actually include, before calling the function, before evaluating, before anything, you can add an if that a equals b, little a equals little b. And if that happens, then you know that all your values in the range are equal, and you can already do that. What do you do with this? Well, that will depend on the precise representation of the function that you're trying to compute. But basically, it means it means there is no cut here, no interesting cut in between. If there is a cut, it might be this one, or it might be to the right, but there is no cut in between because all the values are 7. So if you keep doing that, you will know all of the values of the function, and that is enough to know the cuts. So this is the idea. It is a very simple recursive implementation. Again, the idea is simply that you want to call the recursive function, telling it, okay, compute this range, and I want you to discover the values of the function in this whole range, because basically discovering the values of the function implicitly is the same as discovering all the cuts. It's the same thing in a different way. I want you to find all the values of the function here, knowing that the values themselves are between this value and this value. And you just evaluate in the middle. Well, if your range has only one value, then you don't have to evaluate anything. You know that's the value of the function as a constant there, and that's it. That's the base case. And that's good because basically that's the intuition of why this will be faster. If k is much smaller than n, then as we divide, we're basically dividing at the same time the range of the domain and the range of the values of the function. But since the range of the values is smaller, it will often end up being a single value quicker, and so we hope to span large segments of the domain with the base case where we discover all of these values must be the same because I have the same values on the extremes. So you evaluate in the middle and pass that as the bounds for recursively, and just go like that. So how much will this cost? Now this one is harder to analyze because this is a recursive algorithm in terms of how many queries it does. But basically, if you carefully compute it, you will get to the conclusion that it does k log n divided by k in the worst case. So it's like the best of both worlds. It doesn't have this pesky 2 factor, so it's twice as good in terms of number of queries as the jumping approach. And by now, if you've looked at the previous problems, you will see that twice as much queries is a huge difference because unlike runtime, which is very sensitive to very little changes, in these problems, the judge can very precisely measure how many queries you've done. So it can very precisely ask you to do like 10 less queries. So twice as many is a huge difference. So yeah, this is like an excellent algorithm for this. And compared to the very basic dual lot of binary search, well, it has the same complexity except for this divided by k, which is great because then if k is incredibly small, like for example k equals 1 would be the normal binary search, well, it's basically the same as just doing each binary search, but as the number of k grows larger and larger with respect to n, it gets quite better. Each binary search gets really cheaper in a sense, unlike the basic way where binary searches don't get cheaper. The idea of how to prove it is basically to think about the recursion tree in this case, and what you will see is that every time that the tree branches, this might not be a balanced tree, but every time that the tree branches, you will see that basically you will be dividing the range into 2 sections. And so, well, that means that you cannot branch too much. If you branch too much, because a true branching implies that the sizes of these regions actually decrease. The only way that the regions do not decrease is if you choose very unbalanced. For example, if A was 5 and B was 10, and f of C ends up being like 10, then okay, your left problem will again be 5, 10. It will not be reduced. But in that case, your right problem will be 10, 10, and so it is a leaf in the tree. It immediately returns. So that means that the part up to the leaves, is a tree with at most k times branching, and that is responsible for this k factor over here. You actually, if you ignore those leaf nodes that are immediately solved, you actually get a tree with k nodes. But the other detail is that you could get a lot of branching like this, where okay, these are the nodes that we are actually ignoring, and those what we get is a long paths of branch where we're not actually branching, but we are delaying. Like okay, I evaluated and the range did not decrease. And so. But in that case, the domain is decreasing in half, because you are reducing the domain by half. So eventually you will actually run out of domain, and because of how this algorithm works, eventually you get that if you are going to implement it, you should check that base case too. You might eventually get to a situation where AB specify an empty range, and in that case you can just return. There's nothing to compute. But that might happen because basically if that happens, you've found a cut, because you're being asked to compute a place here, and let's say you're told, okay, A is 5, little a is 5, and B, or let's say little a is 7, little b is 10, and a and b are equal, so specify a range over here which would be empty. But then it means that the cuts between 7 and 10 are right here. So that is where you identify the cuts. When you are asked to compute an empty range, well, an empty range is the same as one specific cut in the array, and these values will tell you what you are cutting actually. Well, and returning to the analysis of complexity, those long branches, so if you see the main tree shape, it will be a tree of k nodes. But this is ignoring these parts where it lengthens without reducing the values. But that can be done at most, at most log n, because you have to reduce the domain in half each time. But well, it is log the length of that branch in the domain, and the sum over all the branches has to give n. So you can check that the worst case is actually when they are equally divided, and that is why you get this n divided by k factor. Basically because, again, the sum of the logarithms is maximized when they are as equally divided as possible. So, well, that was separating binary search, which I think is a very nice idea. It is only, I've only seen it applied actually in this kind of interactive queries problems, because at its root, it's just a slight optimization. I mean, in terms of runtime, it is very unlikely that this will, unless the calling of function f is extremely costly, then in terms of runtime, this makes almost no difference. It's still k log something. Well, that something is slightly less, but still k log something. And logs are typically cheap. But here, since each of these units is is a query, and we pay for each query, and we don't have to exceed that budget, it is critical to reduce it, and this might be necessary to solve some problems. For example, this idea is enough to solve problem price from IOI. Iran was 2017. Okay. Yeah, it is a well-known problem, and this technique solves it beautifully in a very short number of lines of code. And you need for 100 points to do this version. This version, or even this version, won't be enough for 100 points. There are other ways to implement this fancy binary search, let's say, this separating binary search, but I find that this recursive idea of passing the ranges is the clearest. And the code is very short because you just have to check those base cases, like I am in an empty interval, so I found a cat, or a equals little b, so I know that there are no cats in the range and I can return if I am searching for the cats, because all of these values are exactly the same. So those are two little if, then you call recurse, then you evaluate in the middle, that's the only place where you call the query function, and then the two calls. So it's extremely short, much shorter than merge sort or than quicksort, which have a similar pattern. So yeah, I hope you learned something, and good luck on the contest, because I will warn you, there will be interactive problems in the contest. So good luck.